Electrochemical cells. Electrochemical cells are that. It's a way to use a chemical reaction to get electricity. They're also called galvanic cells, after the name of Luigi Galvani, or Voltaic cells after Alessandro Voltano. Those are two Italian scientists from back in the 1700s. And what we're going to learn today is how to draw the cells and some components that go with them. What we're going to do specifically is we're going to learn how to make a zinc copper voltaic cell. We'll use that as an example. So we're going to make these cells in the lab, and you also should be able to draw and label one. So let's start. So the first thing, let's say we're going to make a zinc copper cell. This is a review. You have to go to your reduction table to see where's the reduction going to occur, where's the oxidation. So you see the most positive value is for the zinc, so we know this is a reduction. And the most negative value is zinc, so that's an oxidation. So this is actually going to be written in reverse, and the zinc solid is going to be a reactant, and the zinc ion is going to be the product, so that will be written in reverse. When you do that, what we see here is we'll have these two half reactions, and the overall reaction will be copper solution plus zinc solid will produce a zinc solution and copper solid, and the voltage that goes with that is 110 volts. A couple things that are important about this is that we see the zinc is the oxidation and the copper solution is a reduction. Keep that in mind as we go through the next step. Here we have the zinc and the copper, and they're divided in what we call two half cells. One side is the anode, the other side is the cathode. Now, how do we remember those? Well, one thing you can do is remember the word anode begins with a vowel, and so does the word oxidation. So oxidation always occurs at the anode. If you remember from the previous slide, we said this was the half reaction that would occur at the anode, or the oxidation. If you notice the difference between this and the way it looked in the reduction table, all we did is we wrote this in reverse. And if you look at the cathode, that is a consonant, and we see the reduction begins with a consonant as well. And so at the cathode, we have the same half reaction that we saw written on the reduction table with a 0.34 volts, and we didn't change anything about this at all. Some things that we want to notice here. Well, first of all, you should be able to label the anode and the cathode. So let's start with the anode. What do you put there? Well, you'd have a zinc. So you would have a zinc solid. So there's a piece of zinc solid, and that is your electrode. So there's a piece of metal zinc, and it's in a zinc solution. And on the other side, at the cathode, where we have reduction occurring, we have a copper solution, so that's Cu2+, and then a copper electrode, and that's our cathode. So the cathode could be called, this entire half cell could be called the cathode, or specifically the piece of metal could be called the cathode. And similarly, the anode could be called the piece of metal, or the entire half cell could be called the anode. Now what happens, notice at the anode we have electrons being released. So those electrons will always go from the direction from anode to cathode. Please remember that. That's something you should write down. Electrons will always go from anode to cathode, and we see them going that direction. And so what we'd see at the voltmeter, we should see a reading of the same voltage we saw on the other page. That is the direction of the anions. Also what happens, notice this zinc electrode should be getting smaller because we see the zinc solid is going into solution and creating zinc ions. That's what's happening at the anode. Over at the cathode, however, we have a blue copper solution, and that's actually being deposited on the copper metal. So this electrode is actually getting larger, and this solution should become less blue as copper ions become copper solid. And so the last thing we want to note here is when these two half reactions proceed, they build up a charge. One side builds up a negative charge, the other side builds up a positive charge. So you see the positive charge would occur on the anode side because you're creating a lot of zinc, and the negative charge would occur over where the copper ions are reacting. How do we prevent that? Well, the anions go toward the anode. Notice we have something called a salt bridge here. Salt bridge is important. If you don't have a salt bridge, you're going to build up charge, and so the salt bridge prevents the buildup of charge. And what is in the salt bridge is a material that will migrate to either cathode. So we have anions from the salt bridge will go toward the anode. So you should write that down and remember that anions go toward anode. and the cations will go toward the cathode. Now, what you pick to go in the salt bridge should be something that doesn't react. What we have in this salt bridge is sodium sulfate. So sodium goes in and doesn't react with any of the ions. Sulfate goes in and doesn't react with any of the ions there. But remember, from the salt bridge, anions migrate toward the anode and cations migrate toward the cathode. A couple other things. Galvanic cell can also contain a salt bridge, a porous disc, or it could be the salt bridge. So we see two different variations of what we see for the salt bridge here, a porous disc or a salt bridge. Also, notice the electrochemical process is transferring electrons, and we see there's a reducing agent at the anode, but the electrons here are once again going from your anode to your cathode where you have an oxidizing agent. And let's keep going. And if you were to look and see what's happening here specifically, and if we're able to see the molecules, notice the zinc solid atoms here. Zinc solid atoms are actually becoming zinc ions. So they're going into solution, and this is showing the electrode getting smaller. Over here at the cathode, we see the cathode's getting larger because the copper solution is turning into copper atoms, and those are actually depositing here on the piece of copper. That would be, if we could see the molecules or see them at that level, that's what we would see. The other thing you notice here is we have a reading of voltage, and the voltage is a 110 that we calculated when we combine those two half reactions. And then, of course, here we see this is going to be a porous disc, and so that serves a function of the salt bridge that separates the two cells. And then we'll finish here. This is a final drawing that shows a summary of everything we've done. We've got the voltmeter. Another thing you could put the voltmeter is the actual voltage. It's 1.10 volts, and that's the amount of volts. That's the difference between the zinc and the copper. And you see in the salt bridge we have potassium, so the potassium would be the cation, or that would be the cation, so that would go toward the cathode, which we'd see here. So potassium would go this way, and nitrate would be a negative. It would be an anion, so the nitrate would go toward the anode right there. So you see the zinc electrode, so this is the anode reaction, and that's the cathode reaction. And we wrote the overall cell reaction with the voltage on the second slide. And so that's it. That's a summary of Voltaic cells.